with it. And I decided to do this because I had some conversation in my office with Saul and with Diego, and maybe I think it's that understood. So if you want, this is a set picture. Property A was a choice. Yeah, for any x in the space, you attach a certain subset which is uniformly localized in the space. So let me just put this condition A localization already here. So this guy lives in a ball centered at the point X, yeah, and everything is in X. So let me be a bit sketchy. Don't take the pictures too seriously, but maybe it allows you to understand better what is happening here. So I'm putting X on the horizontal axis here. Of course, X is not R, but just think of it as a, think of it as a simplification. Yeah? And since we can draw only in 2 dimensions on the blackboard, let me put another copy of X here. This set picture tells you that for every X, I'm attaching to this point a subset of the space, which is say here. Yeah, so this is X, and this should be A of X. So I told you yesterday that the important condition is the isoperimetric condition, this relation between boundary and interior. Okay? So if I'm close to X, say 1 here, well then I can attach another set, and I insist don't take it too seriously. This is just an interval, it has nothing to do with R, but I think it allows you to understand better. So if these two guys are close, the intersection of these two sets is very big compared to the symmetric difference, which are the tails that come up here and here. So these two little tails compared to the intersection is small. Now remember again the condition, the important one, the isoperimetric condition. The symmetric difference, these two guys, is small compared with this one. I'm not putting the quantifiers for any epsilon and any r, there is an s, blah, blah. This you have in the notes and you have on your note, in your notes yesterday. So what happens if I'm far away? So I'm far. Well, then my interval is this term. So this would be, okay, so this is the picture. So instead of rushing to nuclearity of sister algebras, which is kind of far away, let me just insist once more on property. Yeah, and then I will tell you what consequences it have without proof, and maybe sometime in future you'll get interested in that. Yeah, so you see this guy here, which is far away from X or Y, at Y prime, yeah, this is disjoint with this one and with this one. Okay, so this is set picture. Okay, we have another one due to the Hickson-Rowe presentation of property A. Yeah, so this is the set picture, and this is the Hilbert space. Vector. Okay. And remember again, what was it? For any point here, for any
Creía que lo que ibas a hacer era no escribir en 2 pizarras distintas. Creía que lo que ibas...
ya. Es que el dibujo es grande. Ok.
Bueno, pues,
Okay, anyway, no problem. I can do this. Okay, so what was the game here? You assign a psi of x, which is a vector in a Hilbert space. I will try to settle the confusion yesterday. So what do you have here? Let me just put again x here. And remember, these guys here were not only vectors on the Hilbert space, but on the unit sphere of the Hilbert space. So let me just intersect with S1. And so you have here x, and to each x you attach a vector. Now think of this kind of a vector bundle, not exactly, because I have no differentiable structure, and in fact the space is uniformly locally finite, so you have a smallest distance, kind of a Heisenberg distance, below which you cannot come close to a point, but never mind. So we attach a sphere, and to this point x, I'm attaching a vector psi of x. Okay? If I'm close to that guy, I will attach another vector. Yeah? The unit sphere, so this is radius 1, P1. And this guy here lives in the same plane. Again, don't take it too seriously, it's just a way of understanding. And these two vectors, this one here and the one I'm going to draw in a minute, are close because these points are close. So say this here. Okay? To this point, I attach this vector here, and to this point, I attach this one here, which is kind of a little bit rotated, and altogether, if you allow me to do a kind of projection here, these two guys so this would be psi y. It's a kind of zoom on both things, and this is psi x. And this guy here is small. This is the difference of both vectors. And remember, the condition was okay, this happens at close points. Great. So, that's convenient. Look here. I can go far away in the same picture. So now I take a y prime there. Now I take a y prime there, and I attach again a vector. But since I'm far away from x and from y, I must be orthogonal. And so I attach again a sphere. This is y prime. And I must be orthogonal to this plane, so I just take a vertical vector. This is and of course, I'm not drawing a fourth vector. This you have to put in your imagination, because I need another. If I'm even further away, I have to attach a vector which is orthogonal to this one, and to this one. So I need an extra dimension. But I have a lot of place, because if you remember, we have a lot of Hilbert space. I can put it in an orthogonal component of the vector. Yeah, so if you want to perceive the picture, this you have to do in your head. Okay. Is it clear now geometrically? So what was the confusion? Yeah. What is the relation between the set picture and the vector picture. Yeah? The space is countable, everything is discrete, countable, etc., etc. And then you can numerate it. And so the vector that corresponds here is just, so if you have an x, which is, I don't know. Remember again, the point x may be in A of x, but does not need to be there. It has to be close to the it must be contained in this ball, the set, but you don't have to have the center. We had that question yesterday. Okay, so if this is x1, x17, and x32, remember, non-empty, infinite, then you can attach the following vector. One, or maybe with our normalization, whatever. Yeah? 0. This corresponds to the point 1. This corresponds to the point 17. And here, this is position x17, and this is position x32, and this is an element of L-theme, which is, if you want, dense in L2 of x. Yeah. So the confusion was to evaluate, as Daniel pointed out. Yeah, but this is a very natural assignment. When I wrote the characteristic function, I was meaning this. I was, without saying it consciously. But I think this is pretty clear now. So what happens with the Hilbert space embedding? A metric space with property A is a coarsely, at large distance, it is a piece of a Hilbert space. So this is a bit more complicated. But I will try to reason again in a picture, and then I stop, and we start with operators. Okay? But in a very relaxed way. Or at least I will try. Can I delete this here? Okay. How about the Hilbert space embedding, or coarse embedding? Now we want to map x, which are points. Remember again, the metric space has no linear structure, nothing, just property A, which is a purely metrical condition. And still you can embed it coarsely into a Hilbert space with orthogonality notions, etc., etc. That's really unbelievable. So what was the, let me just try again with the calculus 1 picture. And so, we have an x, and then we have this vertical axis is not exactly the vertical axis here, not exactly. We have several levels. And here we were quantifying the r's or n's. Yeah? This r is telling you what is close and what is not close. Okay, so at level 1, I attach a vector, Cx. At level 2, remember the precision, the epsilon was scaled again with the n. So depending on what is my radius, which decides what is close and what is far away, I also have a scaling of the precision. Okay, so for n equal 1, so precision 1/2, I have a vector. For precision 1/4, I have another vector, which is closer. Yeah, so here this is psi 1 at x, this is psi 2 at x, and so on and so forth. Yeah? 3, and so on and so forth. Okay. Then I define a reference vector, which was this distinguished kind of the origin, where I have this choice 2. And so on. And of course, if I'm close to that guy here, I'll get another vector, say and here I will have another one. What is the difference between the choices of vectors at level 1 and at level 2? The distance is different. Yeah? So remember, this scaling tells you that at level 1, the vector corresponding to this guy here now the difference of vectors, this little vector here, which is the difference of both, the other way around, I don't care. Yeah. This difference vector is smaller if you raise in the levels. Yeah? So this guy here is 1/2, while the assignment at level 2 is kind of more precise. So the blue vector and the white vector can be more away, while at level 2 they must be closer, or the difference must be smaller. That's the idea. Okay, and so what is this assignment? The assignment is just putting into a Cartesian product, and yesterday there was a big confusion between algebraic Cartesian product and Hilbert Cartesian product. Yeah, and what do you do? What is the map? The map F is just H was the orthogonal sum, and that's very important. That's analysis. Yeah? You not only collect vectors, you collect vectors in a way that the sum of the norms is convergent. Yeah, this is an analytic condition. Little L2 is not the Cartesian product of the spaces. And so what you do essentially, the map is up to a 0, if you want, up to a reference vector here. It is essentially to assigning the whole vertical axis. So you have, if you want, an infinite covering, and you assign all the vectors. You put them together into a Hilbert space. And the idea is just oops. Okay, N1 lives in H1, which allows a bigger tolerance. Whenever you scale, you go deeper into the vertical direction. You are not allowing closed vectors to be too far away. That's the picture. Yeah? And you need this rescaling to prove that the norm of this guy is finite. Yeah? This must be a vector whose norm is finite. Yeah? So let me stop here. Is there any more questions about the picture. At least I think it makes no sense that I rush over this concept, leave it there, more or less understood. I think the pictures, take them not too seriously, but I think they are very illustrative. Okay, and the assignment, and this was a paper, well, not only this, but many more things about Baum-Kohn conjecture, about Baum-Kohn conjecture in Invenciones 15 years ago. So the idea is not easy. Yeah, and the picture is the Hilbert space appears as the Hilbert space sum of all the vectors in the vertical axis. Okay, any other questions? So then let me answer your question on the stability of property A. So property A is okay for partition of a metric space, is okay for Cartesian product. So if two spaces have property A, the Cartesian, the normal algebraic Cartesian product has also property A. Nested sequences of spaces growing, each piece has property A, and that's also property A. The interesting thing is for groups. Remember again, property A for a group is not amenable necessarily. The free groups have property A because they are trees and they're Cayley graphs, but are not amenable. Still, property A is incredibly stable as amenable. So extensions of groups with property A, where the middle groups are A, then the middle group G, so the extreme groups have A, and the quotient has A2, and so on and so forth. I can tell you now more things. Almost as stable as amenable. Yeah? Ref products and many constructions, they are stable under property A. So it's also for groups a very interesting product. Okay, so any more questions on that? Okay, this explanation I will have to sacrifice, yeah.
¿Dónde usamos la bounded geometry?
Sorry?
¿Dónde usamos de hecho que sea espaciométrico una bounded geometry?
Pues lo usamos en el hecho de que estos conjuntos no pueden tener infinitos puntos, que las bolas están uniformemente acotadas, ¿no? Eso lo estamos usando un montón, pero sobre todo va a aparecer en lo que voy a contar ahora, o sea, en la relación entre nuclearidad y propiedad. ¿Vale? Pero yo no puedo, aquí tengo que tener un número finito de puntos, ¿vale? Porque si no, o sea, si tú admites una bola que no es localmente, o sea, si yo admito, por ejemplo, como espacio métrico 1 partido n, cualquier bola en torno a 0 tiene infinitos puntos. Eso no puede ser. ¿Okay? Pero el efecto de bounded geometry empieza ahora, en el capítulo 3.
Pero, hombre, pues yo no acabo de entenderlo cómo podemos aplicar esto a espacios de operadores donde las bolas tienen como muchos elementos. Es como algo que es muy grande comparado con todo lo discreto aquí.
Bueno, la contestación es que bolas no van a bolas. Ahora verás.
Vale.
Ahora verás.
Y si después es separable también sirve eso, ¿no?
¿Perdón?
Es decir, si es separable, o sea, esto es lo mismo, porque al fin y al cabo...
¿Qué significa separable? Numerable, quiero decir.
Sí.
Bueno, el espacio es infinito. Z es un espacio de geometría acotada. Todo grupo discreto finitamente generado está aquí. De hecho, es el prototipo. Y es por eso que tiene interés en teoría de grupos. Numerable va bien. O sea, infinito numerable va bien. No numerable, seguro que también hay gente que trabaja en eso, pero no sé. Yo estoy ya al límite. Y los espacios de Hilbert separables. ¿Okay? Great, so let me just go to chapter 3 to answer your question. Of course, if you read the papers in written form, there are no pictures, no diagrams, nothing. You get the condition, and it's actually what you should do when you read papers, try to translate them into things that make your intuition bigger. Okay, so chapter 3. So light years away from my script. I will do no proof. I will do examples, but no proof, which you can read there. Yeah, and it was a baby version of the script. That's a bit more. Okay, I think the construction you can understand fully. Again, you have bounded geometry. And if you don't want to remember what was that again, just think of a Cayley graph of a finitely generated group. That's the universe. So the construction of the uniform row algebra, actually this was the title of the section, so let me put it here. And this algebra was invented. I don't know if some of you like partial differential operators. There is a Atiyah-Singer index for Laplacians, Hodge Laplacians or Laplacians on a compact Riemannian manifold. And the question was, is there an invariant, a numerical invariant also in the non-compact case? So this algebra was invented to solve this problem. Yeah, I'm not telling you more, but it came from a completely different direction. So I present it to you like a cooking recipe. You have ingredients, say a Hilbert space, which is not kind of abstract, but just very concrete. The Hilbert space is going to be the guy that appeared many, many times here. Yeah? So think of infinite sequences, infinite components. In general, X is infinite. Otherwise, of course, any finite set is amenable, and of course it has a property A and so on and so forth. Yeah, and you have an orthonormal basis here, which I denote by delta X. So to start answering the question of Mark, the question of Mark, the metric space enters through the index set, yeah, labeling my vectors in the space or components in the space, yeah, and this is an orthonormal basis. Of course, delta X is a vector and has infinitely many components. Yeah, it's like orthonormal basis here. It's the canonical orthonormal basis, which has almost everywhere zeros and at position X and Y. Or if you want delta X, well, yeah, that's the picture. I'm not evaluating. I don't dare to evaluate. Okay, so what are operators? Let me see. I prepared. Yeah, operators. What are operators? Well, this is a bit of functional analysis. Yeah, my operators will be bounded operators in this Hilbert space, mapping linearly H to H. And the norm, this is a Banach space for the operator norm. So for those of you that really had no functional analysis through their ways, let me say that if the dimension of if the dimension of H is n, and this guy here, once you fix some, for instance, this orthonormal basis, the canonical one, is just matrices with complex coefficients. Yeah? So if you want, an operator is an abstract guy, mapping vector to vectors, and these are the coordinates of the operator. Once you fix a basis, you can write it in numbers. Okay? So the matrix is the coordinate expression. If the dimension of this guy is infinite, little l2, for instance, well then you have to think of these guys here. If you want, once you fix an orthonormal basis, there is a choice of coordinates. Choice of basis is a choice of coordinates in the geometrical language. So you see that the matrix elements are labeled by points in the metric space. So n, your favorite matrix, maybe the favorite metric space is n. So you have 1, 2, 3, etc. All natural numbers. If you have a double infinite matrix, you have all integers. Yeah, but that's a very convenient way to think about it. Yeah, so T x y. If you want, it's an extended linear algebra to infinite dimensions. This is the matrix element, it's the matrix evaluated, the operator evaluated at the canonical basis. That's the condition. And there is a very interesting notion here where the metric comes into play. The notion of propagation of an operator, and then I will give you a few examples. Okay, so that's an important notion, probably new for most of you, propagation of T. T is an bounded linear operator. Okay. You look at all matrix elements which are different from 0. Yeah, you have an operator, you compute the matrix elements by doing the sandwich here, and then you collect those x and y's for which the matrix component is different from 0. And then you measure the distance between x and y. And then you take the soup. These are non-negative numbers. Maybe the soup is infinite, and then you have infinite propagation. And you call this the propagation of T. Yeah, and let me stop here and do a few examples and pictures and so on. I will not do problems. Well, I will mention one. I will compute for you the propagation of the discrete combinatorial Laplacian on a graph. Yeah. Yeah, let me do some examples. Remember, in my examples, I always try to start with a trivial one. So think of a diagonal operator. So take an infinity function on x, which is an infinite sequence where all the entries are bounded, say a constant sequence. Okay? And then the multiplication operator, oops, is just, if you want, say this way. Yeah? And if you want to write it really as a vector, this is just f x v x, or if you want to numerate, This is the component of the vector on the orthonormal basis delta x2 and so on and so forth. That's a multiplication operator. The matrix representation of this guy is just everything, everywhere else, 0. So it's a diagonal operator. So what are the matrix elements different from 0? Yeah, it's a diagonal. Yeah, it's a diagonal operator. And so the propagation of this multiplication operator is 0. The propagation of an operator is telling you, I move delta x to delta y. If you think on applying the operator to the orthonormal basis, yeah, and you want to know uniformly over all matrix elements how far away you are pushing delta x to delta y. What is the difference between delta x and delta y if this assignment is non-zero? A diagonal operator has propagation 0. Okay. Let me say your metric space is N. Yeah. So my matrices, so my operator, whatever it is, in L2 of N, or little L2, so the Hilbert space would be L2 of N, which is typically denoted by L2. Meaning you have infinite sequences, x1, x2, x3, yeah, or v1, v2, v3, etc. And the matrix elements here are KLs, and now KL. So let me present to you the next, at least from the propagation point of view, the next trivial example. What happens if my operator uniformly sends delta k to delta k plus 1? Yeah, this is the unilateral shift. I'm not saying the unilateral shift is trivial. I'm saying from the propagation point of view, it's the next obvious choice. Yeah. Yeah. Maybe this is a star. So what is the matrix representation? Yeah? What is the matrix representation of this guy here? So S fix the orthonormal basis of little l2, which is 1, 0, 0, 0, 0, 1, 0, 0, 0, etc., is just, of course, nobody's is standing still. No k, ek is sent to ek. So there is a motion, but a uniform motion over the whole Hilbert space. And so you have zeros on the diagonal. I think it's this one here. Yeah. ¿Es este? Bueno, había 50%. Si alguna vez puedes tener suerte también, ¿no? ¿Cómo me dices cómo lo haces tan rápido? Okay, so the propagation of this guy here is final. And the propagation of the unilateral shift is 1. A variation of this operator is the following. It's an exercise in the exercise sheet. I think it is 2 something. 3-1, sorry.
Perdón, es el traspuesto este.
I don't believe. It's this one here. You check.
Míralo para de cero.
¿Estás seguro?
Sí, por ahí.
Bueno, claro, sí. Tampoco está bien. No, está bien, ¿no?
Tiene que ir E1 a E2, ¿no?
E1 a E2, sí.
Entonces, tiene que llevarte el vector 0, 0 a 0, 1, 0, 0, 0. Ah, vale, eso está.
It was right.
Yo lo he dicho por convencimiento, luego por cálculo mal.
Okay, never mind. So you can guess what is the propagation of the adjoint, which was this. The adjoint operator and adjoint for the Hilbert space. Yeah, adjoint. And you compute that the adjoint is just killing the 0 vector. So E1 of the first vector is sent to 0. The second orthonormal basis element is sent to the first. the third to the second, so it's pushing on the other direction. But since I'm starting at 1, there is a kind of boundary, and then E1 is sent to 0. Yeah, and maybe for those of you that are too attached to linear algebra, let me provoke you a bit and say that, yeah. So if you think that any isometry is unitary, then you are really finite dimensional. Yeah? This is the standard example that shows to you that this notion here is an isometry. So you map a vector isometrically to another one. It's an algebraic characterization of an isometry if you want. In linear algebra, you have finite dimensions. This means that the determinant is different from 0, so you have the inverse matrix. But not in infinite dimension. There is no determinant. Well, there are some notions of determinants, but not so trivial one. Yeah. And so you have something where S star S is 1, but S star is 1 minus a one-dimensional rank 1 projection. And that's typical of infinite dimensions. Okay. Let's go for the exercise 3.1. Dime.
La distancia entre los EK, la EK y EK más 1 no es raíz de 2.
La distancia entre K más 1 y K.
Sí, ¿no?
Yo tomo en N la norma euclídea. O sea, vamos a ver.
Sí, la norma es de raíz de 2.
La norma euclídea de N. Esto es 1, ¿no?
Pero la norma de 2.
Ah, no es L2. Es yo cojo N como espacio métrico. Pero bueno, puedes poner si quieres una norma euclídea.
O sea, la distancia no es la que tenía el producto escalar. Es la que te viene del conjunto.
Claro. O sea, lo bonito de esto es que estás mezclando un espacio métrico en las etiquetas, pero esto está bien, ¿no?
Sí, pensaba que la distancia venía del producto escalar del espacio.
No, porque no es un vector, es una etiqueta.
Ya, pero
Estoy etiquetando mis operadores. Ya. Es muy confuso y no dejará de ser al final de la clase. Tenéis que pensar muchas veces. Porque en cierto sentido rompe los prejuicios que uno tiene del grado, ¿no? Las matrices pues están etiquetadas por números naturales, lo normal finitos, y aquí ahora es infinito, y además se pueden separar los puntos. O sea, pero eso es lo nuevo, claro. Okay, so let me do an example and then I'll let you play. Exercise one. So you have a graph. Let's make it simple and connected. And there is a very nice realization of the discrete Laplacian as a really D star D, but I'm not going to enter to that. It's really a discrete version of the Hodge Laplacian in manifolds. It's really nice, but can be topic of a different school. And so the Laplacian, the graph may be infinite. We are not afraid of infinitely many vertices. It's mapping L2 of D to L2 of D. There are also many versions of Laplacians. You have combinatorial, signless, standard Laplacians, blah, blah, blah. Anyone qualifies, so let me take the combinatorial, which is the most usual in discrete mathematics. It's a close friend of the adjacency matrix. So how it is defined? You eat function in here, yeah, function on the vertices, and you evaluate it as v, and you get the degree. We have the degree already, counting at v how many edges go out of v, and you evaluate here, and then you subtract the values. So since the graph is simple, I know if I have two vertices here, so this is v, remember? So this is telling you the vertices that are related by an edge to v. Yeah, so this would be u, this would be a possible u, this would be a possible u also. So u1, u2, u3. Yeah, and so in this case, the degree of v would be 3 in this example. You evaluate, this is a diagonal assignment, and then you assign the value of the function at first neighbors. It's a second order operator like the Laplacian on a manifold, but discrete. And so, what is the propagation? What do you think? What is the propagation?
What is simple? What is a simple graph?
Simple graph is that you don't have loops and multiple edges. So this is not allowed,
Okay.
and this is not allowed. Because otherwise, I don't know, it's the easiest way to, in fact, combinatorialists like to use this simple graphs. Yeah? But in physics and in many places, you have multiple edges and in applications also. Yeah, so I only have to tell you who is related with who, and I know it's only by one edge. If there is a relation, just one. Okay, so what is the propagation? Let me start. What do you think? What do you think? Again, whenever I say my metric space is this one here, but this is the Hilbert space, but what is the metric structure of the graph? This is what I need. It's the path length. Yeah? So remember, we are going one step further. We have the space, the metric space, and now we are doing a construction on that space. But the distance relation is the path length, and the propagation is 1. It's very related to that, because this is a first neighbor. To go from, to have a non-zero, and the adjacency matrix is also 1. To have a non-zero entry in the matrix, I need to be at distance 1 from V. So I'm pushing delta V to delta U1 or delta U2, delta U3, and the distance is 1. Yeah, and also this one. Propagation of the adjacency. I'm not writing it, it's essentially this part here is also 1. Okay, who can guess about an operator with infinite propagation? Who has imagination to think of it? You can already give me, and this is another exercise. How can we send, don't tell me delta 1 is sent to delta infinity. Delta infinity doesn't exist. What do you think?
We can take, for example, the operator S, but instead of SK over EK, we send it to E to EK. So each EK, we send it to E to EK.
Another example?
That goes further and further.
I didn't quite understand, so let me write it for everyone. So you have again this one here, and so your operator is say,
EK,
yeah.
E subscript 2K.
Yeah, very good. Yeah. So you send, this is not uniform anymore. So I'm sending 1 to 2, 2 to 4, 3 to 6. Depending on my K, I will go further away. This is the intuition, and this is the propagation is infinite. Okay? Essentially because 2K minus K is equal to K, and this is unbounded. This goes to infinity. Yeah. Okay, so this is infinite propagation. Okay, I will present to you the construction of the uniform row algebra, 2 lines, and then we stop, and then I tell you a few more things, maybe half an hour or less, 20 minutes, and then we stop and we can answer questions or start comment on everything, or go for lunch. So construction. So if you remember, I stopped the examples and we continue with the receipt. Yeah, we are constructing. By the way, what is the propagation of S squared, the unilateral shift squared? 2. Yeah, so the S to the power n has propagation n. Yeah, because you move the diagonal when you multiply triangular matrices, you move away from the diagonal. And the intuition is let me maybe complete this here. Intuition. The propagation of T is smaller or equal than R. This means that the matrix representation is a band of width R with a cylinder of width R around the diagonal. Yeah, so this means that T is essentially so this is the diagonal and this is R. Here you may have non-zero matrix elements, whatever, and here you have a 0. So it's a bounded operator. This is the prototype of bounded operator with bounded propagation or propagation at most R. Okay, so we continue with the receipt. We construct a star algebra. Remember again, since I deleted it, so you start with this guy here, then you get a Hilbert space, which is little l2 of x, and for free bounded operators and little l2 of x. And of course, here you have a metric, which is the one I gave you. Remember my very first example, which was a bit strange for the first example of a norm space. But I did it for this reason. Yeah, and I think I gave you the version of taking the soup of the unit sphere. Yeah, so this is the norm in H. This is the norm in H. Yeah. So what is the translation algebra? Let me call it R naught. It's not a standard notation, but it's way more simple for me to write it here. I consider all the bounded operators on H such that the propagation is at most R. And this is a vector space, if you want, but it's not an algebra. Yeah? And the point is that if I have S here, propagation 1, the product is not propagation 1. But still, I can just define the algebra in this way. Because when I move from propagation K to propagation, the product will send me again to a bounded propagation. Yeah? And notation in the literature, you will find this notion. But I prefer R naught in honor of John Rowe. And so what is the uniform row algebra? It is called R of X. It's the completion of R naught according to the operator norm. Maybe let me write here operator norm. So you consider polynomials. So think of this guy as being a polynomial. So somebody living here is just a linear combinations of a linear combination of bounded propagation operators. And then you approximate operators in norm by these guys. Yeah, you don't need to have polynomials here. Yeah. This here? It's just notation.
Yeah, but I don't care what I can see.
The U is for uniform?
No, the complex.
Yeah, because the coefficients, these guys here are complex. It's this is notation in the literature. If by chance you see some article or book, for instance, Noah Q's book uses this notation so that you understand that this is my R naught. Yeah? The U is for uniform, the C is because my coefficients, you could take another field if you want, or a ring, whatever. And for this one here, the notation in the literature is, and this is really well established, but I think for the summer course, I can just change it. Okay? So this is another name, but any book you open, if you want to read about that, you will see that notation so that you are not surprised. Okay? But that's for a summer course, a very easy R, and easier to see on the other side. I don't think this C and this C is going to be different on the internet, okay, on the other side. Okay, so this is the algebra, and let me just do a 5 minutes break, and then I will tell you a few properties of this algebra, okay, in 25 minutes. So the title of the course is course geometry, a different course. Groups and operator algebra. So let me just say 20 minutes or 15 minutes, something about operator algebra. And let me introduce it through a really important example for group theory and for C-star algebra theory. Yeah, so if you want, it's not a functor, but still you have a metric space. And somewhere your cooking receipt gives you a C-star algebra. So think of a C-star algebra as a star. Star means adjointness and conjugation of matrix elements. Any operator is an infinite matrix in general, and you have a star operation, which is an involution, antilinear, blah, blah. And so this is a star algebra, and you close it in the norm. So you consider all possible accumulation points and throw them into the new object, which is the closure. Okay, so that's a picture. That's a prototype, or the prototype, because there is a theorem telling you that. That's an example of a C-star algebra. It's a star algebra which is closed under the operator norm. I had a question before, and the student was claiming, why do you use L2 of X? There is a whole line of research working on LP representation and LP uniform row algebras. So you can, of course, choose L1 or L3 or your favorite Banach space here. Yeah, and that's an important topic too. I don't know much, and I will not say it here. Okay, what is the example? Yeah, and that's a very important example that you can also do here. I told you many times that the prototype of metric space is a group, a Cayley graph of a group. Yeah, so think of X being a group. generated by some finite generating set which is symmetric. Okay. So in this case, if we restrict to a group, what is my Hilbert space? Little L2 of the group. Now the group elements Z, or elements in Z2, or elements in the free group, these guys provide the labels for the vectors in their Hilbert space, or for the orthonormal basis. Okay? And then there is a very important object which is called the reduced group C-star algebra, which is strongly linked with the properties of the group. Yeah? So that's, if you like harmonic analysis, so if you think of classical theorems like Peter Weil, if you have a compact Lie group, for instance, then you have there the left regular representation, which contains all irreducible representations. Yeah, exactly with a multiplicity. This is one of the most nice theorems in mathematics, in my opinion. Yeah, that tells you that the left regular representation can be decomposed as a direct sum of irreducible ones, and how many times they appear in the reduction is exactly the dimension of the representing Hilbert space. It's well, there is a notion here also. So that's not compact in general because G is discrete and maybe infinite. But still you have the notion of left regular representation. And that's a map from the group into the unitary operators of H, which is defined just by translation. Yeah, remember a group, a metric space has no product, no linear structure, nothing, but a group has a product, and we can exploit this. Yeah? So this is the unitary operator labeled by G naught, and I claim this is a unitary operator, so this is a unitary matrix, if you want. So it is defined if I can tell you how it acts on the basis, because it's an operator, so I can extend it by linearity. Okay, so it's a translation. If you write this additively, it's exactly what I told you, or similar to the unilateral shift. So you take the basis element delta G, and you set it to another basis element, which is delta of G naught G. I can multiply. Yeah? And you check that this is a unitary matrix. So, and this is a representation. So this is L of G naught to the minus 1. This is exercise. G naught.
Fantástico.
So, in the case of groups, you have a standard Hilbert space, and since you can multiply on the index set, you define this representation, which is exactly, at least for those of you that have heard classical group theory, even this works for finite groups. This is a highly reducible representation that, in case of finite groups or in case of compact Lie groups, contains all irreducible representations of the group. So this is not reducible, sorry, this is reducible, and in the case of compact groups, you have a direct sum of irreducible pieces, kind of minimal building blocks, and so on and so forth. So I have a bunch of unitary operators, and then I can do polynomial linear combination of these guys, and I construct the reduced group C-star. What is it? It is called CR star G. Okay, and it's just, let me write it So you have these operators, you consider linear combinations of those, and then you consider cluster points of this algebraic object. Yeah? So remember, you don't have to take polynomials because the product of two, it's a representation. So LG times LH is L of GH. Yeah, it's a representation of the group. So it's again one of those. So you have to take only linear combinations and then cluster points. And that's the reduced group system. Okay. Exercise 1, exercise 2, which you can see solved in the notes. The left regular representation is bounded geometry. Sorry, it has bounded propagation. So the propagation of this guy here is just the length of the element you are representing by a unitary operator. And since T is finitely generated, this is fine. Maybe it's not so important, or you can check it yourself. This is really easy. Okay.
Can I ask a question?
Sure.
What is meant by T star of this set?
Yeah, it's a lazy shortcut for saying this here means take linear combinations and closure. It's very typical that you start with 17 operators and you want to generate a C-star algebra out of them. You consider products, linear combinations, and everything they can approach with the operator. Right? In this case, these are very convenient because they are representations. So products end up again with one of those operators. Otherwise, you have to take polynomials and then approximate. Oh, this was maybe 3-2. And don't be afraid. So we have several examples of C-star algebras, We had, for instance, the matrices. We have the compact operators on a Hilbert space. We have P of H. We had more special linked to metric spaces or linked to groups. You have, for instance, a reduced group C-star algebra, or you have a uniform row algebra. These are all algebras of operators which are closed in norm and that live in some B of H. Well, B of H lives in itself. The compact lives in here. The matrices, well, they live in itself. This is the B of H for finite dimensions. And these guys live in P of L2 of X. And it is also, yeah, well, never mind. You can show if X is a group, the reduced group C-star algebra is inside the uniform row algebra and inside in here. So these are just examples. But the theory of C-star algebras is incredibly complicated, I would say. In B of H, you can really have monsters inside. Yeah? And one of the main notions, or one of the main aims in research is to try to select conditions that made these monsters or a subclass of monsters tractable. And nuclearity is one of those. Yeah? And always, when you want to understand a complicated object, if you have a finite approximation in some sense, then it's way more easy. Yeah? And nuclearity is one of those notions, which I will only give you a very superficial idea. Okay? So, what is nuclearity? C-star algebra is nuclear. A C-star algebra, say A, and A can be, well, this is nuclear, but this not in general. Yeah, but so a C-star algebra is nuclear. Think the uniform row algebra or the reduced group C-star algebra. If there exists maps PK from the algebra to matrices, and from matrices to the algebra. So you can go down to matrices and then go up again to the algebra in a very special way, such that the following diagram commutes. Yeah? Right?
¿Cómo puede algo no conmutar con la identidad?
Bueno, porque factorizas a través del... Factorizas, estás haciendo algo, ¿no?
O sea, que sea una...
Sí, estos son, perdón, es que no lo he puesto. Y que saqué... Empiezo en el álgebras, volvemos a ir. You cannot understand it as I wrote it, but I will give you just a very quick idea. Time. KDN, muy bien visto. No puedo poner aquí n porque yo no sé si voy a ir con el paso 1 a los números complejos, con el paso 2 a las matrices 2×2. Esa es una...
Eso era porque estaban de las dos.
Pero es al revés, ¿no? Porque esto implica que es de dimensión finita.
No.
¿No? En la composición no es al revés.
A ver, yo no he dicho qué tipo de mapas son, ¿eh? No son isomorfismos, claro.
Pero
son lineales y son unitarios y completamente positivos.
Si eso es la identidad, sí, su K sería selectivo.
¿O no?
Entonces, dimensión de A como espacio vectorial sería menos igual que las matrices que es...
No, porque no es un isomorfismo.
Pero si su
Pero
composición es la identidad...
Esto es lo que se tiene que cumplir. O sea, yo bajo a las matrices. Okay, let me just finish. Okay, because so these guys here. Unital, completely positive. So in my dreams before giving the course, I was I wanted to give you 1 hour lecture on unital completely positive maps, which are linear mappings, are not homomorphisms. So products here do not go. Product here does not go to a product of matrices. It's a linear map. Yeah. It preserves positivity. So a positive definite C-star algebra. Think of linear algebra. Positive definiteness is sent to a positive definite matrix and way back. So you preserve positivity in a very strong way. I'm not telling you, maybe if you like quantum information theory, unit or completely positive maps is the main tool where you use these mapping. So I wanted in the course to introduce unitary or completely positive maps because I think it's very useful not only for us, for describing nuclearity, but they are very, very useful in mathematics, but not this year. Okay, so imagine of nuclearity, and now I'm starting to give you some relations, some proofs. No proofs. Some statements, and you have to believe them. One of it is proved in the notes. Yeah. So there is a think of nuclearity as a kind of finite dimensional approximation. This mapping here is called a non-commutative partition of unity. You have heard in topology the notion of partition of unity. You have a topological space. Let me just that's a purely topological condition, and that's a non-commutative version of that topological condition. In some places you will read that a C-star algebra is a non-commutative topological space. Yeah? And maybe you can get an intuition of what it means. And then I will start telling you what are the relations between the notions we discussed. Analogy, partition of unities, say, oh, X, Z. X is the metric space in this course. Yeah? So you have a collection of functions from topological space, I think 0, 1, such that for each X in the space, Z in the space, there exists a neighborhood such that I think the cardinality of functions related to this neighborhood such that it's different from 0. This guy here must be finite. In other words, for any point, you have a little neighborhood around the point where only finitely many functions are not 0 at that point. Yeah? And so you have that f of x for any x. Yeah? For any I was not prepared for changing the notation. In other words, you can write taking functions from this partition of unity, you can decompose the values between 0 and 1 in the sum of finitely many elements here. Yeah? And this sum is finite. Okay, so this is the non-commutative nuclearity. I didn't tell you what is unitary completely positive. In fact, there are exercises, and some of them are solved even in the notes. But think of this as C-star algebras that have a nice factorization through matrices. Here you have a nice factorization through numbers. So these functions are real functions, and they commute. And the functions here are unitary completely positive maps. Okay, that's not enough. But I think if you understood in the whole course the notion of property A, that's it's more than enough. Yeah, but let me tell you that there is another notion, a kind of non-commutative notion of or partitions of unity. This is standard in a general topology course. And let me now start with the relations. Okay.
Can I ask a question?
Yeah.
The diagram does commute or either does commute?
Asymptotically commute.
Okay.
Only asymptotically. So in this sense. Yeah. You bend. You bend. Sorry. Yeah, so you have kind of linear copies. The linear structure is somehow finite dimensional in a sense. So these maps are non-multiplicative, are not homomorphisms. Star homomorphism are unitar completely positive maps. For instance, any state in B of H is a UCP. Yeah, okay, but you have a nice, and you see this is a quite restrictive condition, and still you have a lot of algebras. There are many monsters, even in the nuclear ones, but still it's more tractable. And so let me delete the analogy. Did you hear about this notion? Yes, I suppose. In topology, yes. And think of a non-commutative version of this. Some facts, results. G is amenable. I mean G, as usual, yeah, is amenable. If and only if the reduced group C star algebra is nuclear. An old result of the 80s. Yeah, so you see, at least for me, the connection between groups and algebras, yeah, it's not just because we like to do complicated things, but you have the fundamental notions, and each side can be equivalent for this class of algebras, the reduced. Yeah, these are completely linked to the group. Yeah, you can see the amenability of the group at this side by checking nuclearity, which is difficult in general, or the other way around. If you can easily check amenability of a complicated group, you know its group C star algebra is going to be nuclear. Second result.
Una duda.
Sí.
Si te dan una esfera de álgebra que no proviene de ningún grupo, pero compruebas que es nuclear, ¿se puede construir algún grupo generado finitamente?
No, en general no. O sea, hay muchos invariantes, ¿no? Y una álgebra, vamos, con probabilidad 1 no va a ser un grupo.
Vale.
O sea, si ya los grupos son complicados, imagínate las estrellas, ¿no? O sea, es un nivel de complejidad. Por eso hacen falta nociones que te orienten un poco en el... Ok. Our metric space has property A, let's say. Then the uniform row algebra is, guess what? Nuclear. Okay, this is a theorem 2002 by Scandalis, and you. Very famous paper, I think, in theorems of Anna, so forth. And then this is a small contribution which we did with some my colleague in Barcelona, La Autónoma, maybe somebody know him. He's amenable as a metric space. So remember again, amenable as a metric space means that you have these Fowler sets that have a nice isoparametric relation, or a very small isoparametric relation. Boundary over inside is small. Then there are many, many more. And guess what? not nuclear. Well, you don't know because we haven't used it. Has traces. So the fact a trace is a linear functional. A trace is a state. If you like physics, it's physicists call them states. It's a positive linear and continuous functional. So this is a Banach space. You may consider functionals on it. And positive linear and continuous functional such that T of AB is the same in T. That's the tracial property. Formulate it in different ways. So T A star A is equal to T A star. That's another equivalent way of telling you. That's like traces in matrices. But even if the matrices don't commute, traces, the value of the trace doesn't care. And these traces also appear in infinite dimensional algebras. And the amenability, the metric space amenability, is equivalent to the existence of traces there. So if you give me, if you are so clever to write down a functional, so a functional is just an element eating operators and splitting numbers, which is linear, which is continuous. Here you have a norm, and here you have a norm. And positive, so positive definite operators are sent to non-negative numbers. Yeah? So a state in the physical sense. And so amenability of the space, metric space amenability, is equivalent to having a trace. And there are many, 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 many more. And I wanted in my dreams to show you that, what did I want to show you? This here. In the case of Coarse. Yeah, and it's a baby version. Remember, amenable implies A. In my very early dreams, I wanted to show you this. But then, as the day came closer and closer, I decided to the baby, and then reality brings me back into an hour. And I think I would like to start here. Yeah. Tell me.
Entonces, si tienes dos espacios que sean A, por ejemplo, X y T, los reducidos estos, los que U asterisquito X. ¿Eso? Entonces son asterisquitos isomorfos.
No. A ver, no te confundas con grupos. O sea, que un espacio, esa es un poco, si el grupo es promediable, entonces tiene la propiedad A. Pero si el espacio métrico es promediable, no tiene por qué tener A. ¿Ok? O sea, la amenabilidad implica propiedad solo en grupos discretos únicamente.
Sí, claro. Que si tienes dos grupos, o sea, dos espacios con A,
sí.
La RO de los espacios, los diferentes espacios,
sí.
Tienen que ser asteriscos de muerte. Sí.
O sea, si XA tiene, si tienes dos espacios y dos álgebras, no tienen por qué ser isomorfas. ¿Por qué?
No, pues sí, tienen A.
Hay muchos espacios no isomorfos que no tienen A. Lo que estás preguntando es por un problema de rigidez. O sea, por ejemplo, si yo tengo dos álgebras de Rho isomorfas, son sus espacios isomorfos, no depende. O sea, no es 1-1, eso es lo que se llama rigidez. Lo muevo un poco una de las partes, las álgebras, no tienen por qué coincidir los espacios. Hay una clase de equivalencia, no tienen que ser isomorfos. En el caso de funciones continuas, sí. O sea, un homeomorfismo de funciones continuas en funciones continuas, perdón, un automorfismo de álgebra de funciones continuas en funciones continuas será un homeomorfismo de espacio. Pero no pasa siempre. O sea, la respuesta es no. A lo mejor no te entiendo bien.
No. La pienso.
Bueno, si quieres lo hablamos más tarde. También estoy aquí la semana que viene. Okay, lo que quiero, what I want to say is that there is really a a strong link between properties of one side and properties of the other. And these are only 3 examples, but there are many, many, many more. Other questions?
¿De quién es el primer resultado?
El último, ese es lo que probamos en
Los últimos tuyos.
pero ahora,
¿Sí, el primero?
dos chicos, dos compañeros. Ahora, Yan Chang-Wu, que está en Texas A&M, y Kang Lee, que está ahora en Barcelona, Alemania.
¿Y el primer resultado?
Bueno, este es muy antiguo. Este es, me parece, Choi Efros. Y no estoy seguro si hicieron ya la equivalencia o solo una y luego se completó. O sea, y hay muchas más propiedades algebraicas que se traducen en propiedades de espacio, de grupos o de lo que sea. Y esto es lo que quería haber hecho. Y una pena. Pero bueno, lo tenéis en las notas. El problema de eso es que hacía falta primero como media hora de aplicaciones completamente positivas. Que os acostumbréis, hay varios ejercicios, pero en fin. Yo creo que tampoco tenía sentido que llegásemos a eso corriendo, ¿no? Por lo menos si tenéis claro lo que es la propiedad A, que es más geométrica, pues ya es mucho en el curso, porque es bastante avanzada, digamos. Ok, bueno, pues nada, un gusto dar el curso.